Hello, this is Richard Hammack's Calculus 1 course. We are in part 2 of the course on limits. Today, lecture 8a is the first in a two-part installment on Introduction to Limits. Previously, in lecture 7, we investigated the problem of finding the slope of a tangent line to the graph of a function, and we realized that the solution involved a new concept called a limit. And our plan was, and still is, to investigate limits thoroughly in part 2 of the course, and then return to tangent line slopes in part 3 of the course. So for now, put tangent lines on hold and look exclusively at limits. What they are, what they mean, and how to find them. At the end of lecture 7, we stated this informal definition. Suppose f is a function and c is a number. Then the limit as x approaches c of f of x is the number that f of x approaches as x approaches c. So this expression, which we read as the limit as x approaches c of f of x, stands for the number that f of x is getting closer and closer to as x gets closer and closer to c. We can draw a picture of that as follows. Here's the graph of f of x, and here is a number c. Now it so happens that for this particular function, f of c is not defined. There's a hole in the graph, which is actually pretty typical in limits. But that hole occurs at a y-coordinate of L. And in this picture, you can see that as x approaches c, f of x approaches the number L, which means, according to our definition, the limit as x approaches c of f of x equals L. So to see that, take a value of x and look at f of x, and now let x approach c and look at what happens to f of x as x approaches c. So x is approaching c, and f of x is getting closer and closer to L. As x approaches the number c, f of x is approaching the number L. If x were to the other side of c, and we look at f of x, it's above L, but as x gets closer and closer to c, f of x is getting closer and closer to L. As x approaches c, f of x approaches L. So L is the number that f of x approaches as x approaches c, which means that L is equal to the limit as x approaches c of f of x. Limit as x approaches c of f of x equals L. I'll draw a slightly different picture of this, and we'll look at it from a slightly different perspective. Here's the same f of x, the same c, and the same L. One way of thinking about the limit as x approaches c of f of x is to just look at what's happening for values of x that are really close to c in some small open interval containing c, and ignore everything else on the graph. Just look at this strip that you get from the x values in this small open interval, and you have this small portion of the graph right here, and you can see that for these x values in that strip, your f of x values are pretty close to L. Your f of x values are very close to L. And I'll put the rest of the graph back there. But the idea here is that you could make this strip containing c smaller and smaller, and those x values inside that strip would correspond to f of x values that get squeezed into L. As this interval gets smaller and smaller and smaller, the corresponding x values in it have y values, f of x, that are getting squeezed into L. So with this picture, we can have a slightly more precise definition of the limit as x approaches c of f of x equals L. It means that you can force f of x to be arbitrarily close to L by restricting x to a small enough open interval around c. So by taking values of x in a small open interval around c, you're forcing f of x to be very close to L. And you can get f of x as close to L as you want. You can guarantee that f of x will be as close to L as you want by choosing this open interval around c with your allowable x values to be small enough. So for any open interval around c, take an x in that open interval, f of x will be up here. And if you want to guarantee that f of x is going to be closer to L, just make this strip here, this open interval, smaller. This is a more precise way of looking at the limit and defining a limit, because it could be that your function f of x looks something like this. It has some rather wild behavior. In this case, notice that as x gets closer and closer to c, f of x is below L, then it goes above L, then below L, above L, below L, above L. It's oscillating back and forth above and below L. So it's not strictly getting closer and closer to L. Sometimes it's going away from L or moving towards L, going away, and so on. But in the long run, as x gets closer and closer to c, your f of x values are zeroing in to L. So the takeaway here really is, as we stated up here, the takeaway is that the limit as x approaches c of f of x is the number L that f of x approaches as x approaches c, with the understanding that f of x could be approaching L, maybe as indicated here in this picture. Not getting steadily closer and closer to L, but going back and forth, but zeroing in on L. As an example, consider f of x equals ln of x squared over x minus 1. Notice that if you try to plug in 1 to f of 1 would be ln of 1 squared divided by 1 minus 1. And ln of 1 is 0, and 1 minus 1 is 0. So you'd get 0 over 0, which is undefined. Well, that's fine. It just simply means that 1 is not in the domain of this f. But imagine you asked yourself the question, what about the limit as x approaches 1 of ln x squared over x minus 1? Let's see if we can find out what this limit is. So here x is approaching a number that's not in the domain of the function. What do you get? What is the function getting closer and closer to? Well, here's a graph of f of x equals ln of x squared divided by x minus 1 that was drawn with the graphing utility. And it has a nice smooth shape. Looks like a nice smooth curve. It has a hole in the graph at x equals 1. Remember that f of 1 wasn't defined, so there's going to be no part of the graph over x equals 1. But otherwise, the graph looks like this. And it so happens that if you graph this really carefully, as I've done here, and you look at it, that hole appears to be at y equals 2. That's its y coordinate. And in this picture, notice that as x gets closer and closer to 1, f of x is going to get closer and closer to this number 2. As x gets closer and closer to 1, f of x gets closer and closer to 2. As x approaches 1, f of x approaches 2. From the other side, as x approaches 1, for this x, f of x is down here, but as x approaches 1, this f of x is going to move up closer and closer to 2. Let's take a look at that. So as x approaches 1, f of x approaches 2. So from this evidence, we would surmise that the limit as x approaches 1 of ln of x squared divided by x minus 2 equals 2. Now we haven't really proved that because is this number really 2? Is the y-coordinate of this whole really 2? Would it instead be 1.999 or something like that? But just from this evidence, it appears that the limit is equal to 2. You could reinforce this if you wanted to with a table tallying x values that progressively get closer and closer to 1, like x equals 0.5, then 0.9, then 0.99, and 0.999, and so on. So 0.5 is here, 0.9 is there, 0.999. It's getting these x values are getting closer and closer to 1. And with a calculator, I've tallied the corresponding ln of x squared divided by x minus 1 numbers. And they start out at 2.77, a little bit bigger than 2. And as x gets closer and closer to 1, these y values, you can see they appear to be getting closer and closer to 2. So that's numeric evidence for the fact that as x approaches 1, f of x approaches 2. That the limit as x approaches 1 of f of x equals 2. The situation illustrated in this example is pretty typical for limits. We have a function f of x and a number 1 that could not be plugged into the function. 1 is kind of a bad point for this function. You try to take f of 1, it's not defined. Yet you can ask what is the limit as x approaches 1 of that function. And here we found that even though we can't plug in 1 to the function, we can take the limit as x approaches 1 of the function and get 2. So limits tell us about what happens to a function near a bad point. They give us information about how the function behaves around these bad points, like 1. And that's going to be very useful for us in calculus. Here's another example. You might recognize this from the previous lecture, lecture 7. Find the limit as x approaches 1 of x squared minus 1 over x minus 1. Notice that 1 is a bad point for this function. If you tried to plug in 1 to x squared minus 1 divided by x minus 1, you'd get 0 over 0, which is undefined. Yet, in this example, we're asking, what is the limit as x approaches 1 of x squared minus 1 over x minus 1? What is the limit of the function as x approaches this bad point, 1, that can't be plugged into the function? What we did last time with this is we noted that the numerator of our function is x squared minus 1, and that factors as a difference of 2 squares, and you get some cancellation. This function, x squared minus 1 divided by x minus 1, simplifies to x plus 1 through cancellation. You have to be kind of careful because this cancellation only works when x is not equal to 1. If x were 1, you'd have 1 minus 1 divided by 1 minus 1, and that would be undefined. It wouldn't be equal to 1, and it wouldn't cancel and give you the x plus 1. You cannot plug 1 into this function because you get 0 over 0. But otherwise, this function simplifies to x plus 1. So let's graph the function, and then we can talk about what its limit is as x approaches 1. If you graph the function x squared minus 1 over x minus 1, that just simplifies to x plus 1, as we indicated here. And x plus 1 is an easy function to graph. That's a straight line, slope 1, y-intercept 1. So it looks like this. But remember, you can't plug in 1 to our function, because if you did, you'd get 0 divided by 0. this cancellation only works here for x not equal to 1. So at x equals 1, there's a hole in the graph. And that hole occurs at a y-coordinate of, it happens to be 2, because that y-coordinate is 1 plus 1, x equals 1, and y is 1 plus 1, which is 2. And you can see here that if you take a little narrow strip around x equals 1, the number that x is approaching in this limit, your corresponding f of x values for these x values, they're going to be around 2. And as you make this open interval smaller and smaller, those corresponding f of x values get closer and closer to 2. So as x approaches 1, f of x is approaching 2. So the answer to our question is the limit as x approaches 1 of x squared minus 1 over x minus 1 is 2. As x gets closer and closer to 1, we can see that x squared minus 1 over x minus 1 is getting closer and closer to 2. And that's even more evident because this quotient simplified to x plus 1. So this limit is the limit as x approaches 1 of x plus 1. And it should be pretty clear there that what you're getting is 2. As x approaches 1, x plus 1 would have to approach 1 plus 1, which is 2. So here on this page, we have several ways of looking at the fact that the limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. More examples. Graphed is a function y equals f of x, and let's see if we can work out these limits. First of all, the limit as x approaches minus 5 of f of x. Well, here is minus 5, and let's look at this by taking a narrow strip through minus 5, and just looking at the graph around that narrow strip, which would be this little portion here. And I think you can see that as x gets closer and closer to 5, f of x is getting closer and closer to the y-coordinate of this hole in the graph, which looks like it's negative 1.5. So we would at least estimate that this limit as x approaches minus 5 of f of x is minus 1.5. For the limit as x approaches minus 4 of f of x, here is minus 4. Let's take a narrow strip around minus 4. And there, if you just look at that portion of the graph for those x values, you can see that as x gets closer and closer to minus 4, f of x is just going down to 0. So the limit as x approaches minus 4 of f of x equals 0. And then the limit as x approaches 2 of f of x. Well, here's 2. Look at a narrow strip around 2, and you can see that when x is close to 2, our f of x values, they are really close to 2 as well, y-coordinates of 2. And the closer and closer x gets to 2, the closer and closer f of x gets to 2. So the limit as x approaches 2 of f of x equals 2. For another example, think about the function f of x equals 1 over x squared, and it's graphed here. And look at the limit as x approaches 0 of 1 over x squared. Now in this case, as x gets closer and closer to 0, f of x is just getting bigger and bigger and bigger and bigger. In fact, if you take a narrow strip around 0 and look at the graph, I don't care how narrow that strip is, you're going to get parts of the graph inside this gray rectangle that just keep going up and up and up and up without bound. So here, f of x is not approaching any single number as x approaches 0. It's going to infinity. So because as x goes to 0, 1 over x squared doesn't approach a finite number, in this case, we have to say that this limit does not exist. And that can happen for some limits. They will sometimes not exist. And we will abbreviate does not exist with the letters D and E. That stands for does not exist. So the limit as x approaches 0 of 1 over x squared does not exist. I'll show you another example of a limit that doesn't exist. This one involves the function y equals sine of 1 over x, which is graphed here. And it has an interesting graph. As x gets closer and closer to 0, the graph just oscillates back and forth between y equals -1 and 1, with the oscillations becoming tighter and tighter as x gets closer and closer to 0. And that makes sense because as x approaches 0, its reciprocal 1 over x is getting bigger and bigger and bigger. So sine of that is just oscillating up and down. So as x gets closer and closer to 0, sine of 1 over x bounces up and down between -1 and 1, oscillating faster and faster and faster the closer and closer and closer x gets to 0. So because sine of x, or sine of 1 over x, is not approaching any single number as x approaches 0, we would have to say that the limit as x approaches 0 of sine of 1 over x does not exist. In our next example, we'll modify this example very slightly by multiplying the sine of 1 over x times x to get a new function, y equals x times sine of 1 over x. And if you think about what happens there, in multiplying by x, when x is small, close to 0, it's going to scale down these y values that are between -1 and 1 to make them closer to 0. And the function looks like this. Here's the graph of y equals x sine 1 over x. And think about the limit as x approaches 0 of x sine 1 over x. The function's oscillating positive and negative as x gets closer and closer to 0, but it's getting closer and closer to 0. Here we have the limit as x approaches 0 of x sine 1 over x equals 0. So on this page, we've seen numerous examples of limits that exist and that don't exist. It's important that you read the text and work lots of exercises to make sure you have a good grip on this. Let's move on to a related topic, left and right hand limits. I have the graph of a function y equals f of x here, and you can see it has a break in it. And we're asking, what is the limit as x approaches 3 of f of x? That seems a little bit problematic because as x approaches 3 from the right, f of x is getting closer and closer to 4. But as x approaches 3 from the left, f of x is getting closer and closer to 2. A limit has to be a single number. It can't be equal to two numbers. What are we going to say this limit is? Limit as x goes to 3 of f of x equals 4, or 2, or the average of 4 and 2? Actually, in a situation like this, we have to say this limit does not exist, because f of x is not approaching a single number. We can salvage some information from this picture by creating what we call a right-hand limit. In this notation, there's a superscript of plus next to the 3. And we read this as the limit as x approaches 3 from the right. That superscript plus means that you are insisting that x approach 3 from the right. We read this as the limit as x approaches 3 from the right of f of x. And it's understood that this means, or stands for, the number that f of x is approaching as x is approaching 3 from the right. And you can see here that as x goes to 3 from the right, f of x approaches 4. So the limit as x approaches 3 from the right of f of x equals 4. Similarly, we're going to define what's called a left-hand limit. Superscripting the 3 with a negative means that we are restricting x to approach 3 from the left. And we read this as the limit as x approaches 3 from the left of f of x. And that value is 2, as you can see here. As x goes to 3 from the left, f of x approaches 2. So these are called right-hand limits and left-hand limits. The limit as x approaches c from the right of f of x is the number that f of x approaches as x approaches c from the right. And the limit as x approaches c from the left of f of x is the number that f of x approaches as x approaches c from the left. And it's a fact that in order for the limit as x approaches c of f of x to be equal to L, the right and left-hand limits as x approaches c of f of x, they also both have to be equal to the same number L. Otherwise, the limit as x approaches c of f of x doesn't exist. And that's illustrated in the picture here. So get some practice with right-hand limits and left-hand limits, work some exercises in the book, and we'll see this idea pop up from time to time as we go through this course. So that's it for today. Coming up next, the second installment of Lecture 8. Lecture 8b is on limit laws, which are algebraic rules that help us compute limits efficiently and quickly. I'll see you there. Goodbye.